Okay, so I want to talk about one thing that is kind of my secret weapon and something I've developed to help myself think about these complex systems, which are the aquariums and ecosystems that I build, and the closed ones, the open ones, the aquariums, and what have you, anything like that. They're all called complex systems, and I employ systems thinking when I um, go about troubleshooting and thinking um, about the system. First, I want to talk about complex systems. It's very important to know this because it is the reason why this entire universe has something in it and not nothing. It's the way abiotic, non biological entities, meaning objects, atoms, volcanoes, tectonic plates, galaxies, stars, organize themselves. It, of course, wasn't random. They're complex systems, and complex systems are unique in that they display nonlinearity. They have emergence characteristics, meaning one of their components within the complex system component kind of performs a process or a function for the system, can have emergence. It can develop something that no other component has, basically out of nowhere. It can exhibit spontaneous order. Emergence is one way it does that. Also, it can self-organize and self-configure itself. Our little systems here, they they self-organize in what's called ecological succession, and it takes about 30 days, which is why cycling a tank takes about that long. They also can adapt, and the most important thing about complex systems is that they have feedback loops. Feedback loops is the reason why they can adapt in the first place. For example, they need to be able to take input and put output out to the environment. They need to take the result of that output, the effect it had on the environment, and they need to be able to process that as more input and then send out the output from that once again. And then because of complex relationships between the environment and the system, those interactions will develop changes in behavior and changes in inputs, which will change the outputs, which will affect the environment, which will change the system. And through a kind of natural selection of abiotic forms, you'll have complexity emerge out of seemingly non-biological systems, and that is how they will gain complexity over time. Okay, so what is systems thinking? So, in event-oriented thinking, you have in event-oriented thinking, everything can be explained by causal chains of events. Systems thinking heavily focuses on feedback loops because these systems are complex and feedback loops are a major part of it. Just think of your aquarium, of your gerarium, whatever kind of aquatic thing with plants you're growing, whatever you call it, I don't know. That is a complex system, and there's a lot of feedback loops going on. That's why it can catch people up, because one thing affects the other thing, which can affect this thing, but if that thing's low, it could cause something else, whereas, another person might have low this, but it's causing another problem. These are all feedback loops, and they can get kind of complicated. So, in systems theory, we have archetypes of feedback loops. And these are good to know, although I don't know them. I just kind of know how the system works, and these are kind of good to know because you can spot these feedback loops and act on them. Some more properties of complex systems. Let's see, I kind of snapped this. Organization, information processing, dynamics, evolution, and learning. And these are traits of biological and abiotic complex systems, because everything in the universe is either a component to a complex system or a complex system itself. And here is the reason why we're so damn afraid of robots and artificial intelligence. Here is a cybernetic loop. Notice the similarity? That's right. You have the sensor, you have the controller, and you have the other system. This is basically like the same exact thing of a complex system. Except the scary thing is, AI can process feedback millions and millions of times a second. And that equates to millions and millions of little changes. and adaptations. And that is the scary thing with artificial intelligence and cybernetics at the fundamental level. Here's a ecological model I made of my aquariums, my little systems, to make it easier for customers to kind of get an idea of what's going on. As you can see on the left, light comes in, goes to the primary producers, goes directly to primary consumers, secondary consumers, and then you can see the various flows of carbon throughout the system and basically energy as well. And as you can see, if you decrease a compartment, which is what they're called, on one, you lower the compartment of CO2, that's going to affect how the primary producers, the plants, produce oxygen, which is then going to affect how that, the decomposers decompose, which will affect this and will affect that, and it gets rather confusing. Okay. Thanks for watching, guys. Next, I might make a video going into more detail about complex systems and how knowing more about those types of systems and, in particular, systems thinking can really aid you in whatever hobby you have, and in life in general. It's just really good knowledge to have. I'll also make additional videos about two things called the constructal law and the maximum power principle. The image you see before you right now is a list of certain characteristics that your ecosystem or aquarium or terrarium, closed or open, will display before it reaches a steady state. That is, before it goes through ecological succession, the first 30 days of self-configuring and self-organization that complex systems go through, and what kind of characteristics a system like that has once it's gone through ecological succession successfully and has reached a steady state. The system changes greatly, and it's good to know those differences, so check it out.